My dear students, today, today we'll see the concept of half-wave dipole. So already I explained to you in the last class, that is video 7. We are having the concept of half-wave dipole. So once again today, so I will give a brief view of half-wave dipole and the quarter-wave monopole. I will share the screen now. So half-wave dipole antenna. So it is having two poles. Therefore, it is called half-wave dipole antenna. So let us come to the contents of this today's session. So introduction and working and parameters and applications, advantages, disadvantages of this half-wave dipole antenna. So just the introduction. So it is the antenna. It is having a length lambda by 2. Let us see. This antenna is having a length of lambda by 2 from this end to this end, or from the tip of this antenna to the opposite tip of this antenna. That means from here to here, there is a length equal to lambda by 2. So therefore, this is called half wave antenna, and it is having two poles. This is one pole, and on the other side, this is another pole. Therefore, this is called dipole antenna. Okay. So an antenna is an electrical device which converts electrical power into electromagnetic waves or vice versa. The half-wave dipole antenna consists of two identical conductive elements such as metal rods which are bilaterally symmetrical. Okay, let us see, this structure is symmetrical with respect to the center position. So this is called feed position. So feed position sense we are applying the power to the antenna at the center. Okay, therefore this is called center fed antenna. Since we are applying the power at the center of this antenna, therefore this is called center fed antenna. This is called the feed. What is called feed? The feeding is nothing but applying the input power to the antenna is nothing but feeding. Okay. And similarly, the half wave term means that the length of this dipole antenna is equal to half wave length at the frequency of operation. Okay. So working, let us see. So that antenna can be briefly represented like this. This is the feeder cable. So this is called the feeder cable. Okay. So this is one pole and this is another pole. Okay. Therefore, this is called dipole. And from this end to this end, the length is equal to lambda by 2. Therefore, it is written as half wave length. Since the total length is lambda by 2, on this side, the length will be equal to lambda by 4. On the other side of this feeder cable, the length is equal to lambda by 4. So therefore, lambda by 4 plus lambda by 4 will become lambda by 2. Okay. So we are applying the power at the center. So therefore, this is called center fed antenna. So that means with the help of a cable, we are applying the power at the center of the antenna. Okay. So why we apply the power at the center of the antenna, we will see in the coming slides. So it is basically fed at the center where the impedance falls to the lowest. Since the impedance is lowest at the center, so we are feeding this antenna at the center, since the impedance value at the center is lowest. So why it is lowest, we will see in the coming slides. The voltage and current levels vary along the length of the radiating section of the antenna. So therefore, let us see in this slide. Here, this is the distribution of the current. This is the distribution of the current. Uh, and similarly, this is the distribution of the voltage. So therefore, this red color region will represent the distribution of the voltage, and this green color region will represent the distribution of the current. So let us see at the center what is happening. At the center, the current is maximum and voltage is minimum. Voltage is almost minimum. So therefore, the what is impedance? So impedance is generally ratio of voltage to current. Okay. So if you take the ratio of voltage to current here, so here voltage is minimum and current is maximum. So therefore, minimum value divided by maximum value, minimum value divided by maximum value. So that is giving minimum value. So therefore, the ratio of voltage to current is an impedance, and that impedance is coming out as minimum value by maximum value. So therefore, at the center we find minimum impedance. So therefore, since there is minimum impedance at the center, so we are feeding the antenna at the center. We are feeding the antenna with the help of a cable at the center. Therefore, it is called center-fed antenna. So generally, it is having a radiation resistance of 73 ohms. So that also will be coming in a derivation in the second unit. Okay, the radiation resistance of this half-wave dipole antenna is 73 ohms. Okay, so that is an important derivation that will be seen in the next unit, that is second unit. Okay, so the voltage and current levels vary along the length of the radiating section of the antenna. So for dipole antenna, that is an electrical half wavelength line. That means it is electrically the length is equal to lambda by 2. The inductive and capacitive reactances cancel each other, and the antenna is becoming a resonant antenna. So due to the cancellation of these inductive and capacitive reactances, so this can be seen as a resonant antenna. So therefore, half wave dipole antenna, these are the distributions of the current and voltage. Since the impedance is minimum at the center, so therefore we are applying the input power to the antenna with the help of a cable at the center. So that is only the reason that why this is called center-fed antenna. The people will be asking why this is called center-fed antenna. Why we have to apply the power at the center only? Like that, the people will be asking the questions. Then you have to tell them that this is the current distribution and this is the voltage distribution, and the voltage is minimum and current is maximum at this position. So therefore, ratio of voltage to current is minimum. So therefore, it is presenting minimum impedance at the center. Therefore, we are applying the power at the center. Therefore, it is called center-fed antenna. Like that, you have to answer. Let us see. A half-wave dipole antenna is receiving power from radio wave. The electric field of the, here let us say here the electric field is represented by green arrows, pushes the electrons in the antenna back and forth. The charging the ends of the antenna alternately positive and negative. Since the antenna is half wavelength line at the radio waves frequency, it is it excites standing waves of the standing wave along the length of the antenna. These oscillating currents flow down the transmission line into the radio receiver. The actions showed in this animation. Okay, that means here you notice that the current, let us say the current, if you see the current distribution, the arrows are in this direction. But in this half cycle, the arrows are in the opposite direction. That means here the charges are moved back and forth. This force will move the charges in this direction, but this force will move the charges in the opposite direction. So in this way, along the length of the antenna, the charges are moving back and forth. Okay, due to the electric field, they are moving back and forth. So since there is back and forth motion of the charges, automatically this is acting as a radiator. Okay. So in any conductor, if there is back and forth motion of charges, then automatically it will be acting as a radiator. That means it is producing electromagnetic waves. Okay. So working. Let us see the working of this half wave dipole antenna. Here we are applying the input power to the antenna at the center. That means it is a center fed antenna. We are connecting a generator here. So this generator will supply the input power to this antenna. Okay. The distribution of the voltage or current is sinusoidal in nature. So the radiation pattern. In this slide you will see the parameters, different parameters. That means what is the directivity and what is the bandwidth. Okay. So what is the radiation resistance? Like that we will see here. And what is the type of radiation pattern that will be seen in this slide. So this is the radiation pattern of this particular antenna. Okay, assume this half wave dipole antenna is at the center. Around the antenna, there is this type of distribution of the electric field around this antenna. Okay, so therefore the distribution of the electric field and magnetic field around this antenna is seen as this type of pattern. So it is an omnidirectional pattern. Okay. So in horizontal plane, it is radiating uniformly, and in the vertical plane, the radiation is not uniform. Okay. So this type of pattern is called omnidirectional radiation pattern. So that is seen in the previous classes. Okay. Horizontally, it is radiating uniformly, and vertically, it is not radiating uniformly. Okay. So here it is somewhat less when compared to the uh, radiation at this position. So therefore, gradually it is decreasing vertically. Vertically it is decreasing. It is becoming maximum here. It is becoming minimum. So in this way, the variation of the field is non-uniform. Therefore, in the vertical direction there is non-uniform field, and in the horizontal direction there is uniform field. So that type of radiation pattern is called omnidirectional radiation pattern. Okay, that means if you cut this pattern horizontally, that means if you cut this pattern horizontally, that means in this way, so you will get a circular pattern. So if you cut this pattern vertically, automatically you will get a figure of eight pattern. So that also will be seen in the coming slides. The directivity of this half wave dipole is equal to 1.64. So when 1.64 is converted into decibels, the directivity can be seen as 2.1 dB. Okay. Actually, it is d equal to 1.64. It is a dimensional less quantity. So when it is converted into decibels, it is equal to 2.1 dB. So the standard ratio bandwidth is equal to 5% of the design frequency. So the polarization is both vertical and horizontal. Okay. And radiation resistance is equal to 73 ohms. Okay. applications of this half wave dipole antenna. What are the applications? The applications are set-top TV antenna, and it is used in FM broadcast receiving antennas and shortwave antenna. It is also used as a shortwave antenna, and it is used in dipole towers and dipole arrays. Okay. So what are the advantages of this antenna? So it is receiving balanced signals. It receives balanced signals. So most of the radiating signal is transmitted closer to the horizon. So therefore, loss is less, and also it does not require an antenna tuner to work efficiently. Okay, and the coming to the disadvantage of this antenna. So generally, it is requiring a balun, BALUN. So what is called balun? Balanced to unbalanced. Balanced to unbalanced is called balun. So balanced to unbalanced conversion is needed here. So coming to the picture of this one. So in order to feed this antenna, so we require a balun. It means normally a coaxial cable, if you see, it is unbalanced transmission line. Okay, so we cannot connect directly the coaxial cable to this half wave dipole antenna. It is because it is unbalanced transmission line, but it requires a balanced transmission line. It is because it is fed at the center. So since it is a center fed antenna, a balanced transmission line must be connected here. So our coaxial cable will not be connected. It is because unbalanced transmission line. So therefore, in order to connect our coaxial cable here, so we require a balun. Okay, so we will connect a balun, and with that we can connect our coaxial cable to this antenna. Okay, that means balanced to unbalanced conversion must be needed. So I will show the picture of the balun also. Okay, what is balun? Balanced to unbalanced converter. Okay, so that will show you the picture in the coming slides of that balun also. So let us see the disadvantage. So that is one main point. That is disadvantage. The main disadvantage is that it requires a balun in order to connect a coaxial cable to this half wave dipole antenna. So the other disadvantages are the outdoors antennas are large and wide. So this type of antenna is not used for space communications, and the installation of outdoor antennas are difficult. Okay. So now I will show you the balun. Okay, in the coming slides. So before that, I will introduce the half wave dipole. The half of the half wave dipole. The half of the half wave dipole is nothing but lambda by 4 in its length. That means lambda by 2 divided by 2. So that will become lambda by 4. So let us come to this half wave dipole antenna. So here, if you see from here to here, there is the length is equal to lambda by 2. Okay. So if you take only half of the length, so that is equal to lambda by 4. So this is lambda by 4 and this is lambda by 4. So if you keep the lower portion of this antenna inside the ground, assume that this lower portion of this antenna is kept in the inside the ground. So if the lower portion of this antenna is kept inside the ground, so you can see only the upper portion. The upper portion is only of the length lambda by 4. That means the lower portion of lambda by 4 length is buried in the ground, and only the upper portion of lambda by 4 is only seen over the ground. Okay. So if you assume like that, automatically So that type of antenna is called quarter wave monopole antenna. Okay, that means the bottom portion is inside the ground, only the upper portion is above the ground. So above the ground, we are looking only the length equal to lambda by 4. So therefore, this is called quarter wave monopole antenna. That will become quarter wave monopole antenna. So I will show that antenna also in the coming slides. And this half wave dipole antenna is also called hedge antenna. Half wave dipole antenna is also called hedge antenna, and this quarter wave monopole antenna is called Marconi antenna. So that will be seen now. So let us see here. So this is a dipole antenna. So it is having a length lambda by 4 plus lambda by 4. Okay. So actually what is happening is that so inside a dipole antenna, so there are many more Hedgian dipoles. The Hedgian dipoles are very small. The dipoles. So this is one dipole. This is one more dipole. This is one more dipole. So and all these dipoles are connected end to end. Okay. So when these very small the current elements are connected from end to end, automatically we are getting a dipole antenna like this. Okay. So here each and every element is called a current element. This is one current element, this is another current element, this is another current element. So it is the Hedgian dipole antenna is nothing but a current element. Here the distribution of the current in this Hedgian dipole is assumed to be constant. Okay, it is very small length. The length is of the order of less than lambda by 10. The length of this Hedgian dipole is of the order of less than lambda by 10. So in this way, these Hedgian dipoles are connected end to end, and these will form the antenna like this. So now in the coming unit, in the second unit, we will see the radiation resistance of this current element. The other name is Hedgian dipole. So what is its value? So that will be seen in the unit 2. So just we are visualizing this entire antenna as end-to-end connection of Hedgian dipoles. Okay, there are finite length elements. So these finite length elements, when connected to end, these will form this entire antenna. Okay, so these all these expressions will be in the coming units. Okay, so let us see here in this slide. So there is a comparison is made between the monopole and dipole. Okay, so that means if you see a dipole antenna is having a radiation resistance of 73 ohms. That is already told to you. Okay. Automatically, what happens for monopole antenna? So this monopole antenna is having a length lambda by 4. That means half of the length of the half-wave dipole. Since length is made to half of its value of the dipole antenna, automatically radiation resistance is also becoming half. Okay, since automatically this radiation resistance of this monopole antenna is nothing but half of the radiation resistance of the dipole antenna. So dipole antenna is having its radiation resistance equal to 73 ohms. So therefore 73 ohms divided by 2. So that is becoming 36.5 ohms for monopole antenna. Okay, so that is radiation resistance of monopole antenna. So that is seen as 36.5 ohms. So that is shown here. So radiation resistance RR of monopole antenna is equal to 0.5 of the radiation resistance of dipole antenna. That means RR of dipole antenna divided by 2. Okay, so 1 by 2 is seen as 0.5. So therefore, radiation resistance of monopole antenna is equal to half that of the radiation resistance of the dipole antenna. Okay, so if you see, the radiation pattern, of the monopole antenna is also half that of the radiation pattern of the dipole antenna. So it is because in the previously we have seen the radiation pattern of this half wave dipole as let us see the radiation pattern is this type of radiation pattern that we have seen for dipole antenna. So since monopole antenna is only half that of the dipole antenna, since the lower portion is assumed that it is kept inside the ground. Okay, only the top portion is present. Since top portion is present, only the radiation pattern is seen as half that of this pattern. That means if you cut this radiation pattern horizontally, it is if it is made into two halves, automatically the upper half is only seen physically. Since the radiation pattern is half that of the radiation pattern of the dipole antenna, automatic radiation resistance is also half that of the dipole antenna. Okay, in that way, the radiation resistance of this monopole antenna is seen as only 36.5 ohms. And similarly, if you see, come to the directivity. So, what is the directivity of this monopole antenna? It is twice the directivity of the dipole antenna. Why it is twice the directivity of the dipole antenna? If you see, the radiation pattern of this monopole antenna is half that of the dipole antenna. So, since the radiation pattern is becoming half, automatically if radiation pattern is becoming half, the half power beam width is also becoming half. If half power beam width is becoming half, automatically the directivity is doubled. So previously in the previous class we have seen directivity and beam width both are inversely proportional. If beam width is becoming half, automatically directivity is going to be doubled. So in this way, the directivity of the monopole antenna is becoming double that of the dipole antenna. DA stands for dipole. And we come to the impedance of this monopole antenna, input impedance of this monopole antenna. The input impedance is also half that of the input impedance of the dipole antenna. Since the distribution of the voltage is also becoming half, therefore the ratio of voltage to current if you take that is equal to 0.5 of input impedance of the dipole antenna. So in this way, the comparison between the characteristics of the dipole antenna and monopole antenna can be made here. Okay. So let us say this is called balun, balanced to unbalanced transmission line. So physically, the balun, physically it can be seen like this, balanced to unbalanced transmission line. That means these two ends are connected to the half wave dipole at the center. So on this side, we are connecting a coaxial cable. Okay, so that picture can also be seen here. Come to the slide. Okay, uh, So these two are connected to the center of the half wave dipole, and on this side we are connecting a coaxial cable. So that will be seen in the coming slides. Okay, and also I told you that this half wave dipole antenna is called Hertz antenna. So Hertz antenna and this the monopole antenna. That means the quarter wave monopole antenna is called Marconi antenna. Okay, so come to this the Hertz antenna. That means the dipole antenna. So the Professor Henry Hedge made the first radio transmission in 1886 in the laboratory of the Karlsruhe University. Let us see, from here to here, it is lambda by 2 in length. So physically, you see, just it is only 95% of lambda by 2. Okay, some 5% is less than lambda by 2 physically. Okay, but generally, we will be telling that it is half wavelength line from this end to this end. Okay, so actually, if you correctly see, the physically it is only 95% of lambda by 2. Okay, somewhat a little bit less than lambda by 2 physically. So this is the construction of this half-wave dipole antenna from the end, from this end to this end. So it is uh, length equal to lambda by 2. So this is called hedge antenna. So it is same. Uh, there is no difference. Just I am showing that this is called, this dipole antenna is called hedge antenna. The radiation pattern of this half-wave dipole antenna or hedge antenna is vertically. If you cut the radiation pattern, automatically you will get a figure of 8 pattern automatically. So for monopole antenna, that means the Marconi antenna, the radiation pattern is somewhat more directional. Okay, if you see, the beam width is decreasing here. Here beam width is more, but here the beam width is automatically less. If there is less beam width, automatically directivity is more. Less beam width, the directivity is more. So on these two sides, it is somewhat elongated when compared to this radiation pattern. So if it is elongated, automatically the directivity is increasing. So that we can see. So the gain of this half-wave dipole antenna or hedge antenna is 2.1 decibels. Okay. So antenna is placed perpendicular or vertically with respect to the earth surface. It is normal used for small applications and was used in the set-top TV antennas. Already we have seen the applications of this half-wave dipole antenna, and the other name for this antenna is hedge antenna, that already seen the previous slides. Now coming to the monopole antenna. So let us see here. So the top portion is of the length lambda by 4. The bottom portion, you have to assume that this bottom portion is kept inside the ground. Okay. So this ground is acting as this reflecting plane. This ground is acting as a reflecting plane for this antenna. So therefore, whatever the antenna that is there on the above on the ground is seen inside the ground. Okay. So this ground is acting as a mirror. Okay. So it is operated on the principle of this image concept. Okay. Image concept in the sense, if there is uh, upward arrow in its image in the mirror, it is seen as a downward arrow. So if there is an arrow moving in the right side in its image in the mirror, it is seen as an arrow pointing towards the left side. So that is nothing but the concept of the image in the mirror. So most commercial vertical antenna is known as Marconi antenna. So when compared to the dipole antenna, the people will be preferring this monopole antenna. Okay, it is because if you take the dipole antenna, it requires a balloon. So it is an extra, like an extra device that the balloon is required for dipole antenna. But here for this monopole antenna, uh, that means the Marconi antenna requires no balloon. Directly we can connect the coaxial cable here without the need of balloon. Okay, we can connect directly the coaxial line without the need of the balloon. So that is the merit that is there in this antenna, and also the directivity of this antenna is double that of the directivity of the monopole antenna. So therefore, generally this is preferred for high gain applications. So physically, it is generally it is lambda by 4 in its length, that is seen over the ground only, and actually physically it is having a 95% of lambda by 4. That means a little bit less when compared to lambda by 4. Normally the people will be telling that from this end to the here the length is equal to lambda by 4. Therefore, this is called quarter wave monopole antenna. The other name is Marconi antenna, or simply it is called monopole antenna. So radiation pattern. This is radiation pattern, and let us see here. The radiation is half that of the dipole antenna. So therefore, radiation resistance is also half that of the dipole antenna. So therefore, 73 by 2 ohms is equal to 36.5 ohms. So this is about the design. It's not necessary for us. Of course, the length is length in terms of frequency, operating frequency. It can be taken like this. Not necessary for us. So used in the radio broadcasting transmitters of high power. Okay. So electrically, Marconi antenna operates as hedge antenna. Physically, it is only a 1/4 wavelength long, and also don't confuse that hedge antenna is not same as that of hedge and dipole. Okay, hedge antenna is not same as that of hedge and dipole. So hedge and dipole is a dipole whose length is very very small. It is of the order of less than lambda by 10. So that is different. So any antenna is assumed as the end-to-end connection of the hedge and dipoles. So previously you have seen that also. Okay. So the arrows are connected end to end previously. So with this I will stop the share.